Welcome to our discussion of z-scores, sometimes referred to as standardized scores. And basically, we're continuing to put together our puzzle with the familiar pieces of means and standard deviations. And we're going to find out we can put those together into an equation and come up with z-scores. So we'll find a bunch of things that we can do with these. And gets us closer to the idea of statistics. We're not doing inferential statistics just yet, but we're sort of building up the pieces, and then we have to change the logic a little bit from those pieces to go further. But it's important to understand and not skip this step either. As we'll find out, z-scores are very important themselves because it gives us a familiarity with starting to think about the mean and standard deviation together into this new unit and start to get us familiar and comfortable with transferring and converting scores, which is basically we're taking raw scores and we're putting them into a new metric, in this case z, or standardized. So what we'll do is we'll do a quick review of what we covered previously about variability. We'll talk about z-scores conceptually. We'll talk about how to use them. We'll talk about what it means to standardize scores. And finally, we'll talk about how we can use z-scores for the most important part, making comparisons. So instead of just saying something is bigger or smaller, using central tendency to make our arguments, once we fold in central tendency and variability together into something such as a z-score, we can even have more certainty about the classic comparing apples to oranges. We don't have to compare apples and oranges if we convert them into the same unit. So first of all, let's get our review of Chapter 4 going. Let's see how much we remember from that. Three main measures of variability. Of course, the standard deviation we want to use, but also we have our range and our interquartile range and those variations too. What is a deviation score? Really, this is important because we are taking a raw score, an x score, and then subtracting the mean from that. And of course, some scores are higher than the mean, some scores are lower than the mean, so a deviation score could be positive or negative, and it's important to keep track of those positives and negatives as we calculate a set of deviation scores from a set of raw scores. It's also important to remember the steps in calculating the variance and the standard deviation. First, we do the variance and then standard deviation. Why do we square and unsquare? Well, because of that mathematical law that if we subtract the mean from a set of scores and add up those deviation scores or deviation from the mean scores, we get 0. So we want that metric to be useful and not nothing. So then we take those deviation scores and square them. And then we add up those squared deviations. That gives us our sum of squares. Then we divide by the sample size. That gives us our variance, or for each score, what's the average squared bounce around the mean, and what does that mean? Squared bounce around the mean. Let's go back to unsquared units, standard deviation, and then we have our standard or average deviation. So of course, just like a set of scores, we calculate a mean and we find the average of the set of scores. Standard deviation is just the average variability or the average bouncing around of a set of scores. Are they sticking close to that average, low standard deviation, or are they bouncing really high and low from that average, a high standard deviation? Degrees of freedom, basically, they're the number of scores that are free to vary. And anytime we do inferential statistic, we are losing a degree of freedom because we're estimating from a sample of scores what we infer a population might look like. But for our purposes, usually degrees of freedom is the sample. How many is it? One sample, and then in that case, if it's one sample, we take our sample size minus 1. In the future, if we have multiple samples, we'll take our sample size minus if we have 2 samples, for example. So anyway, degrees of freedom for now is basically n minus 1, and we'll build on that as we incorporate more samples instead of just one sample in the future. And finally, we have our nomenclature. What do the following symbols mean? SS is our sum of squares. our sum of squared deviation scores. What is this? This is our variance, which is our standard deviation, population standard deviation symbol squared. So we're in our squared units. That means we're in variance units. And then, of course, we have our population standard deviation symbol here. So that is our population standard deviation. And of course, we're not always dealing with populations. We may be dealing with samples. This is our sample variance. And if we want to get into unsquared units, then we just go to our sample standard deviation, take the square root of the variance to get our sample standard deviation. Now let's introduce z-scores. And for our overview, what are we doing with a z-score? What's the goal? How do we use them? Well, basically, we're incorporating the standard deviation into a score that reflects a raw score. So we're just in the process of converting. So first of all, we have a set of scores. We can calculate the mean or the average of those scores. Oh, then we can also calculate the standard deviation. Then we can put those together and to get a z-score for each raw score in the sample. The main question that this allows us to answer that is less convincing without including both the mean and standard deviation is how extreme or typical a value is. So it's not just how far away from the mean is a score. That is a partially good way to determine whether it's an outlier or not. But if we calculate the average bounce around the mean, standard deviation, if there's a lot of bouncing around the mean, a high standard deviation, well then one single score that's far from the mean doesn't look that extreme because all the scores are bouncing around the mean a lot. And the opposite holds true if there's a low standard deviation. If a score is really close to the mean, but all the other scores are pretty close to the mean too, we don't think that's much of an outlier either. So why do we do this in real life? For example, not just if somebody has a high score or a high number of check marks for diagnostic characteristics, do they have a high number relative to the average number? We also think about selecting the best person for the job. We don't just have someone who scores a lot of points and decide to give them a very expensive NBA contract. We want to know, is that person scoring a lot of high points or a lot of points and compared to other people? So is it just this person scores high, but relative to other people, they're scoring high as well? Or is it really sticking out? And also, anytime we're identifying people and making decisions about them, typically we don't want to just look at the mean. We want to incorporate the mean and the standard deviation, and we want to think in standardized or Z units. So here's one example for diagnoses. This might be an initial step in a screening for a clinical sample. Probably would need a person who has a degree to actually make the diagnosis, but this could be helpful for an initial screen. The MMPI is a very highly researched instrument, and you can see that we can break it down between males and females and a bunch of these different subscales. And to get, in this case, we're in K correction, T scores. So we're talking about Z scores today, but you can have other converted scores as well. But the key is we want to consider both the mean and the standard deviation to get to, for example, our T scores that we might actually use to make our diagnoses. Here's another example. If we think about the employment selection context, the Wonderlic is a very popular basically mental ability, general mental ability, cognitive ability test that you can administer usually in less than 15 minutes. And then we can see for different job types, we want to incorporate both the mean and the standard deviation. And with these units, or with these pieces of information of central tendency and variability, then we could calculate z-scores. And then we could then compare, not just do engineers, for example, score higher than lab technicians. We can see that they do, but we also want to factor in, as we'll find out, the variability to be even more sure that engineers are meaningfully higher than, for example, computer operators in terms of Wonderlic scores. And finally, one other example, anytime we think of a standardized test, in some ways we are thinking in standardized scores or converted scores. So we're not looking at necessarily raw scores of how many questions did you get right, for example, or tasks. This is the Denver Developmental Screening Test, commonly used for particularly motor development for children, to see if someone is very advanced or behind in all these different dimensions, but it also includes some social and language examples as well. And so this Denver Developmental Screening Test is useful because it's been used for a long time and it has so much data that we are pretty sure that that reference sample is going to be representative of the population of any student that we test now. That gives us the best faith in being able to make comparisons to what we're seeing in this child compared to what is normal for children of that age. And of course, once again, the lesson here is we're thinking in standardized units that incorporate both the central tendency and the variability, mean and standard deviation. So to be even more specific, let's try and compare scores and think about how this logic works. Well, we see Bob has a GPA of 3.2, Mary has a GPA of 3.4. If we're just using the raw score to make a decision, we would choose to admit Mary more likely than Bob. Are we satisfied with that decision with this information? We would like to actually have more than just the raw score. Let's look at actually the mean and the standard deviation from the population of people at these different colleges. And now we can see that Bob's GPA is actually higher than the average, whereas Mary's GPA is lower than the average. And then, well, how much is the average bounce around that mean? We want to consider this too, but now we've got like a raw score, a mean. For example, we have a raw score, we have central tendency numbers, and we can kind of compare the raw score relative to the average. But then now we got this third thing, variability, to fold in, and now it starts to get a little confusing. But you can see the basic issue. The more information that we consider, the less obvious the decision is. And in this case, with just the raw scores, we take Mary, but then when we consider the population parameters, now it's looking like Bob is the better candidate. So what is the moral of this story? The raw score is something that we understand, especially if it's in units that we're used to using, such as GPA or dollars or pounds or miles. But by itself, it really isn't that useful. We want to have more information. And so this is why we've been building up to think about what does the mean mean, what does the standard deviation mean, why do we want to be able to use these pieces if we can justify, if the data looks good enough, is normal enough, is symmetrical enough or close to it, unimodal. If the data looks good enough and it's appropriate to use the mean and standard deviation, we're going to because we can incorporate them in this way to calculate z-scores or other standardized or converted scores. So basically what this means is if we're comparing two people, it's somewhat useful to compare the raw scores, but it's a lot more useful and we can be more certain about what we're doing if we incorporate the mean and the standard deviation too. So another example is we're looking at a raw score of 76 compared to a mean of 70. Is that a big difference or not a big difference? Well, it depends on what the average difference is, or the standard deviation. In this case, with a small standard deviation, that difference of the raw score to the average of 6 points looks pretty big. If the average deviation or standard deviation is big, in this case 12, that 6-point difference from raw score to mean doesn't seem to look as big. So this is how we want to consider the raw score relative to the mean, also taking consideration the average difference from the mean of the set of scores. Once we have those 3 pieces of information, then we can use all that to look at z-scores, and we can just have one score that can tell us this information instead of having to consider all 3. So let's look at z-scores and their locations and distributions. We started that with the previous slide, but we can build on that even further. First of all, let's think about what standardization means. Basically, standardization or standardized scores means converting raw scores into a similar unit. This is the purpose of z-scores. So for example, let's say we're comparing apples and oranges. We're comparing player performance from one college football conference to another college football conference. One guy has more touchdowns than the other. Which is the better player? Well, just the raw score isn't necessarily going to tell us with confidence which is the better player. So let's put them into the same unit, convert them into the same conference statistics, so to speak, which is the logic of z-scores. Instead of comparing to apples to oranges, we are converting them to the same unit, and so we can be more confident about making comparisons, meaningful comparisons. And you can see, as the logic we've been building up, with a z-score, we can know which is a big apple and a big orange because they're both put on the same metric. We know, oranges, I don't know, are about the same size as apples or a little bit smaller, or how much variability is there a lot bigger range between the biggest and smallest apple compared to the biggest and smallest orange? If we just convert them into the same unit, then we can, if we're picking out a piece of fruit, for example, if we're thinking in standardized units, we know for sure which one is bigger in terms of z-scores. So we'll have a lot more examples moving forward as well. And finally, just working through the example again, is a score of 45, raw score, high or low? Well, we don't really know. Even if we compare it to an average, we don't know if we don't know the standard deviation or variability as well. So having said all that, let's go into z-score. Officially, what is a z-score? It's basically the number of standard deviations a score is from the mean. So if somebody has a z-score of 1, that means that they are exactly 1 standard deviation above the mean. -1, 1 standard deviation below the mean. And you can see here's the formula, fairly simple. So first we take our raw score, in this case our x value, subtract the mean. So we're just taking a deviation score here, but now we're taking that deviation score, dividing by the standard deviation, and now we've converted that raw score into a z unit or a z-score. So of course the sign is very important. So when we're converting, we need to think about what do the new units tell us. So for example, if we're looking at average points per game of different players in the NBA, well, you can't ever score negative points per game. The lowest you can score or average is 0 points per game. But once we convert to z units, the mean becomes 0. And of course, then you can be below the mean if you're below the average and have a negative z-score. So once we've considered the sign, now we need to consider the magnitude, or how big that z-score is. That tells us whether it's positive or negative, how far or above or below the mean that individual score is. So if we look at location in a distribution, a z-score provides the exact location of the score in the distribution, as we'll see many examples coming up. But think about this. Two distributions, both have a mean of 70, and both have a population standard deviation of, one has population standard deviation of 3, the other has a population standard deviation of 12. We had a slide showing this previously. And bringing that back up, with our raw score of x of 76, we know that this x score looks like it's substantially above the mean when the standard deviation is small, but not meaningfully above the mean when the standard deviation is big. So think about the formula that we would use. What is the z-score? X minus the mean. So we have a deviation score of 6. And if we take that deviation score divided by a standard deviation of 3, we get a z-score of 2. So this x is exactly 2 standard deviations above the mean. Now for this one, we take that same deviation score but divide by 12 standard deviation. 6 divided by 12 is 0.5, so that means our z-score is exactly half a standard deviation above the mean of 70. So, once more, note that for every z distribution, the mean is 0. Values above the mean are positive, values below the mean are negative. And the exact value of the z-scores tells you how many standard deviations that raw score was above or below the mean. So let's do some practice problems. What is the z-score for each of the following? And remember to pop this into our formula. But it is our x-score, raw score, minus our mean, divided by our population standard deviation. So in this case, we have 10 minus 8, which is 2 over 2 for a z-score of +1. Our next example, 85 minus 70, 15 over 10 gives us a z-score of positive 1.5. Now we have 25 minus 35, so this raw score is below the mean, so we know that the z-score is going to be negative. Negative 10 divided by 5 gives us a z-score of -2. What else can we do with z-scores? Well, we can work backwards. If we have the z-score and we want to find the raw score, we can go back to our z-score equation. So if we just rearrange this z-score formula to isolate the raw score, which in this case, we have the z-score, we have the population mean and standard deviation. We're looking to find the x. We just bring the standard deviation over, multiply by both sides. So now we've got this, and then we add the population mean. So we've isolated the x. So then what is our score here? We can see that our z 2.2 times our population standard deviation of 100 gives us 220, plus our population mean of 500 gives us the raw score of 700 on this person's math SAT. So once again, the raw score of 720 on the math SAT. Is this good or bad? Well, I don't know. Well, we know it's above the population mean, so we know that's good. Okay, but how far above? Well, we need to consider the population standard deviation. And so calculating or figuring those in, now we know that the z-score is 2.2. So Tom's math SAT raw score of 720 is 2.2 standard deviations above the mean, which we're going to find out is usually pretty good. It's a meaningful difference, meaningfully above the population average. So let's do a little bit more practice isolating the x. So in this case, what is our x raw score? With a z of 0.5, negative 0.5, that is. So first of all, we need to multiply our z-score by our population standard deviation. So that gives us a -1. And then we add our population mean, which gives us a x of 9. Again, using the formula from the last slide, working through. If you do the math, you get x equals 77.5 raw score. And then the final test, again, we multiply both sides by our population standard deviation, bring that over. So our z of 2.5, and then we add our mean, which gives us a raw score of 5.5. So again, just working through the formula gives us our values. And finally, let's think about a little bit larger scale picture of what we're actually doing when we standardize a set of scores onto a z distribution. So instead of just individual scores, we can standardize the entire set of scores. So in this case, we would take the distribution of raw scores, the property of the mean being 100 and the population standard deviation being 10, and through that z-score formula for each score in this population of scores, we can transform them or convert them into z-scores or z-units. So now they are standardized scores, all on the distribution now as anything that's a raw score, whatever that mean and that standard deviation was before. Once we convert it to z, it's all in the same units. So this might be how we think about currency, monetary currency. How different is $100 to 100 yen to 100 kroner? We have all these different currencies for different countries, and it's hard to keep track of what's a big number, what's a small number. If we just convert them all to z units, they're all in the same metric. So in that case, we know if we have, for example, a z-score for our annual income of 2.5, we know that our annual income is 2.5 standard deviations above the average. And that's already been converted. It doesn't matter whether it's in dollars or yen or euros. We've converted it to z-scores, and we know that 2.5 above the 2.5 standard deviations above the average, is a pretty meaningfully difference above that average. We knew if in that case, if that's our income, 2.5 standard deviations above the average, we're doing pretty well relative to the other people in our population. So what happens when we make this conversion? First of all, the shape of the distribution doesn't change. So what this means is if our data was not ideal in raw units or x values, it's still not going to be ideal. In this case, some sort of skew or extreme outliers. They're still going to be there, but instead of raw units, now they're z units. So the important thing is it doesn't change anyone's position in the distribution. If someone is an extreme outlier below the mean in raw or x values, they're still going to be an extreme outlier in z units. Also, the mean of the z distribution is always 0, and the standard deviation is always 1. And again, that's the value of taking units in raw units that are very different, such as currencies or performance in different sports leagues, and then converting them into Z, and now those differences in raw scores and variability from these strange other units are all converted into the same standard one, and we can make meaningful comparisons once we've got those scores all on the same Z unit. They're all speaking the same language, so to speak. And then finally, it's useful to use Z-scores to make comparisons. So for example, when we convert scores, we may want to use involve Z in one way or another. So for example, Bob has a raw score of 60 on his psych and 56 on his bio. Which one did he do better on? Well, just the raw score of 60 may sound better, and if you don't know anything else, well, that's the best we can do. But if we do know things like the population mean and standard deviation, that will give us a better solution to answer this question. So what we do is convert both of these raw scores into Z-scores. And we can see that with Bob's psych exam, we take his raw score of 60 minus the mean, 10, divided by standard deviation 10. He's got a Z-score of 1. So we know that, yes, he's above the mean. He's 1 standard deviation above the mean once we convert to Z units. Now, 56, Bob is also above the mean. Okay, so we know he's going to have a positive Z-score, but how positive is it going to be? Raw score 56 minus population mean of 48, 8, divided by our population standard deviation of 4 gives us a Z-score of 2. So Z-score of psych is 1, Z-score of bio is 2. With this extra information and converting to Z units, we can confidently say that relative to the different populations of psych exam takers and bio exam takers, Bob did better, 2 standard deviations better compared to 1 standard deviation better than the mean on his biology. So just working those out from the last slide, again, we can see Bob's Z-score in psych was +1, and his score on biology was +2. So he should be more proud of his biology score because it was more standard deviations above the population average. So as we wrap things up, let's do a quick review. So population with these mean and standard deviation values is transformed into Z-scores. What will these properties be for the new Z distribution? And that answer is going to be A, Z always has a mean of 0 and a standard deviation of 1. When would a score 15 points above the mean be considered an extreme score? Well, a score that is this many units above the mean will look like a bigger difference under what scenario? When the average difference is very small. And what's another way to say the average difference? Standard deviation, the average deviation. And when the average deviation is very small, on average scores are not bouncing very far around the mean, that makes that this one score, being really far from the mean, look a lot more extreme. So in this case, D would be the correct answer. Let's see if we can convert from Z-score to raw score. So in this case, go back to the formula, but we would take our Z-score, divide by our population standard deviation. That would give us 4, and then we add our mean, and that would give us a raw score or X value of 64. And also consider, what does this mean? We don't even have to do the formula. A z-score of 0.5 means it's half a standard deviation above the mean. Well, we have our standard deviation. What is half of that? 4. Half a standard deviation above the mean is 60 plus 4. So 2 ways to get to 64, through logic or just punching it in the formula. Either way gives us the same answer. And finally, let's wrap up with some true-false. Every X value that is less than the population mean, when converted to Z, will have a negative Z-score. That is true, absolutely. Now, number 2, any population of scores, at least one individual have a Z-score of 0. That is false. Think about, in this case, we're looking for average points per game. We have an average of 29.3 average points per game. Does that mean that in a game somebody scored 29.3 points? Nope, that's not even possible in that case, because you can't score points in decimals. So just because you have an average doesn't mean that an average of 0 in particular, that there has to be an exact z-score that is 0. It's just saying what the average is in z distribution. Now let's look to number 3. If 2 individuals have identical X scores from that population, that population has the same or only one mean and standard deviation, so use those to convert that identical X score, then yes, true, the Z scores will be identical as well. And then finally, transforming the entire distribution of raw scores into Z scores will not change the shape. This is also true. So once again, Z-score is really useful because we can compare apples and orange units on one standard scale, but if the raw scores come from a problematic, especially from a skewed perspective or outliers perspective, just converting those into Z units does not take away the skewness or the outliers in that set of scores. So having said all that, we've gotten through our Z-score logic. And you can see, hopefully, the linkage between all the stuff we've been putting together, particularly thinking about central tendency and variability, how to put those together and make meaningful conclusions about comparisons and data. So again, hopefully that logic makes sense, and we'll be building on that, of course, moving forward as we move from basically more standard statistics into inferential statistics, which is where we want to go. We're not quite there yet, but we're building up the logic to do so. Looking forward to discussing this and much more in the discussions as well.